So hi everyone, today we'll try to understand can autoencoders be used for generative modeling for generating images similar to GANs, and if not, what can be a solution to that? So first of all, let's understand what is an autoencoder in very short. So an autoencoder consists of two neural networks. One is an encoder, other is a decoder. So the whole idea of autoencoder is that we feed in some input X, we take it to a very low dimension called as a bottleness compressed data, and eventually using the decoder network, we are trying to again regain that original input. So the input expected input is assume that to be an image X, and final output is also the same what was an input. So hence we input an X, it get compressed, its representation gets compressed, and eventually the decoder tries to regain the same value as an output. So first of all, let's understand how this can be useful. So let's go through an example. You take a paper, paper sheet A. You folded this paper several times to produce a compressed version of the sheet. Call it as B. Now you again unfolded the sheet to get to its original form, that is A. Now one thing that you have missed in this whole process is that though you have got a similar version of A, but you haven't got the exact sheet A that you insert, that you perform the operation earlier. So now the sheet has some creases. So now you can say that the new version that you have got after unfolding the page is similar to the first version, but it is not the same as the first version. So now in generative modeling also, this is the whole idea that we wish to have. We wish to generate similar images but not exact images or exact embeddings, whatever we are trying to generate. So can autoencoders be used for generative modeling? Maybe yes. Because they can generate similar but not same copies. Works well for complex datasets as well, like images or embeddings, etc. So but how does this happens, how does it will help us in generating images? So the whole concept of autoencoders is based on latent space. So the compression that is happening in the middle, you saw between encoder and decoder network, is that is called as a latent space, in which we are trying to represent very complex data in a very small dimension. So something sort of PCA you can think of. So in PCA, if you remember dimension reduction, what the whole idea of dimension reduction is that we're trying to reduce the complexity, keeping the most important information out of the data set intact. You might miss out on small info, like minor information, and you might not be able to regain the exact copy, but again the crux of the data, the important features of the data would always be preserved. So this is the whole idea of latent space. Hence that is why autoencoders can be used for generative modeling as well. Let's see how. But there is a couple of things that we need to know first. So basically, how can autoencoder may be used, is that we first train it on some image data set, and eventually we detach the encoder part. So it's just the decoder, because you can understand, right, it is a decoder that is generating the final output and not the encoder. So we would be inputting something from the latent space to the decoder, and the decoder should be able to should be able to generate similar samples from a data set on which the encoder decoder combo has been trained. I think so far it is correct. Now let's understand a few points on which this whole problem might go wrong. Let's understand why autoencoders, exactly in the same way that we know, can't be used straight away as generative modeling but require a few tweaks. So we'll talk about the tweaks later, but first of all understand the problem. So as I told you that only the decoder part can be used to generate new samples from the trained data set. But what would be the input? As I told you that it would be some random sample from the latent space, but we don't know the latent space, right? Because eventually, if you have read about autoencoders a bit, so we input some image X into encoder, it get compressed, and eventually decoder is outputting that. So we are not able to see what is the compressed space in which that compression is taking place. How does that distribution looks like? We don't have that idea. So we can't pick up random values and input it to the decoder and expect it to generate samples, right? So one point is that we need to have some meaningful space, some meaningful sample space from which we can pick out values, and then we know that okay, it would be able to generate some value, it would be able to generate some meaningful images or embeddings that on which the training that would look similar to the training data set that we have trained already. Now the second point on which autoencoder miss out is that it also misses out on continuity. So basically assume that we have somehow figured out, okay, this is the latent space. from which we need to pick up the values. If this is the known sample space, if I pick up a value from this, I would be able to generate some similar samples. Now assume that it to be a value from, assume we are inputting -2 comma minus 0.1. This is the latent space representation, and we got an reconstructed image similar to the looking to the data set. Now what we need the model to learn is that if we make slight tweaks to the value, if we instead of -2, as you can see in the image, we do -1.9, we do -1.5, we do -1.4, we might do 1.6, and we might do in the second value as -0.40, -0.6. Then also the decoder should be able to regenerate some image, though it can be of poor quality. But again, you're trying to make sense. What we're trying to say is that there should be some association, some idea to the model that if values are close to each other in this particular space, it should be able to detect, it would be able to give some meaningful output. But in case of autoencoders, this might not happen. The third problem that we might face, so this gives us an idea that the latent space is mostly discrete and not continuous. So discrete means that at a point we might get an output, but if we move slightly here and there, the output becomes bogus. Now the third point is that if we have multiple classes coming in the training sample, for example, we have trained our autoencoder for MNIST datasets, which has 10 digits, right? Now, out of these 10 digits, it might be the case that the latent space for some particular variable, some particular class is very big, and for others it might be very small. Latent space, like again, distribution size. So it can be the case that when you're picking up some value from this particular latent space, only a single dominant class is getting generated again and again, and the generative modeling, the iterative generative modeling, is biased towards other digits as their latent space that has been trained, that we have generated after training from using encoder and decoder architecture, is very small. So it can be the case that the decoder may become a bit partial towards the dominant class, which has a bigger latent space distribution, and eventually only a single class, or say multiple classes, only a few classes are getting dominantly generated every time. So these are three problems that we might face, and that is why the whole idea of variational autoencoders came into the picture, that I will be discussing in my next video. So hence, autoencoders can't be used directly for generating for generative modeling, though there is a variation for that, that is called as variational autoencoders, that can be used for generative modeling.